Well, good morning. It's 10 o'clock, so let's get started. My name is Pat Whitcomb. I'll be delivering your webinar today, and we'll be talking about the difference between repeats and replicates. Since there's many attendees, I'm going to have you all muted, but if you have questions, you can use the questions feature on GoToWebinar and type in your questions. And today we'll have Sherry Kraber will be monitoring for questions and attending the webinar, and she'll be answering your questions. If you think of questions after the webinar, you can send them to us, and I'll have a slide at the end detailing that. So let's get started. So what we'll be going through today is we'll talk about the difference between replicates and repeats. So when we talk about replicates, we're talking about replicating a run in your designed experiment. When we talk about repeats, what we're going to be talking about is repeating a measurement at a single run. Okay, so why would you want to use replicates where you replicate the whole run? We'll talk about the reason why, and we'll bring in a brief discussion of power, and then we'll have an example showing how to use a replicated design. Then we'll talk about repeats, where we're talking about repeating the measurement at a single run in the DOE and why you'd want to do that. And again, we'll have an example to illustrate that. Then I'll recap what we talked about. So let's define what we mean by replicates and repeats. So a replicate is when we're running the exact same settings more than once. So a run in our design is replicated. It's randomized and run at a different time. So we'll be changing the settings in between the replicate runs. A repeat is when we have one run, but we make multiple measures at that run, and we enter the average for the response. So when we talk about replicates, there's basically two ways you could do it. You could replicate the whole design. So you could take the design and say, okay, I'm going to do this whole design multiple times. I'm going to do it 2 times. I'm going to do it 3 times. Why would you do that? Well, replicating the design is usually done to increase power. So we can detect smaller effects or detect effects with greater confidence. Now, a benefit of replicating the design is we also get an estimate of the pure error. So the estimate of pure error means we don't have to make any assumptions. We can estimate the error directly because we're trying to do the same experiment more than once. Replicating the design also reduces our prediction error, so we can predict better in our design space. Point replication is again replicating runs, but we're not necessarily replicating all the runs. They also provide us with an estimate of pure error. They also increase power, but to a lesser extent than replicating the whole design does. They can be chosen to reduce the overall prediction errors. Often replicates at a point are chosen for other reasons, such as replicating a center point in a factorial to have the ability to detect curvature, or replicating standard conditions that exist in the design space to have a reference to what was done in the past. So this would be an example of a 2 to the 3rd experiment. So we have 9 combinations. And when we replicate the design, that means we're going to do each of those combinations twice. So now we have 18 runs. Now those 18 runs would be completely randomized, and you'd be doing the same set of conditions twice, but at different times with other runs in between. An example of point replication might be a 2-level factorial, or excuse me, the again, the 3-level design, so the 2 to the 3rd design, where now we've decided to replicate the center point to get a better estimate of curvature, to be able to detect curvature. And we've replicated the vertices, since those are the most extreme combinations. They have the highest leverage. They also have the highest prediction error. So by replicating those, we reduce the prediction error at these extremes. So remember, a replicate is a new run. Now, if when we randomize the design, it turns out that a replicate follows the exact same conditions, so we're replicating run number 3, and we do run number 1, run number 5, run number 3, then we do run number 3 again. Well, because they happen to come next to each other doesn't mean you can measure twice. That wouldn't capture the experimental error present in resetting the factor settings. So remember, when we say we're controlling factors in a DOE, so we're controlling temperature, we're really not controlling temperature directly, we're controlling the set point for temperature. And every time we change the controls to a different temperature, it varies around that set point. It's not that temperature exactly. And so what we'd want to do if 2 replicates occur to each other is treat them as 2 independent runs, just like we're doing a new set of experiments. And we do everything that we do after a normal set of experiments. If that requires cleaning the equipment between runs, we do that. If it means we have to recalibrate things we're measuring with, we do that. If the factor settings aren't changed, we'd still want to turn the knob away from that present setting and try to turn it back to that setting so we capture the variation around the set point. So all the runs should have exactly the same setup, whether they're 2 separate runs or it happens that they're 2 runs that are the same conditions. Okay, so why would we replicate a design? Well, we're going to have a brief discussion of power. By the way, there are other webinars that are more dedicated to explaining power that you can find on our website. But what I'll do here is have a brief discussion. So basically, when we run an experiment, we're looking to see if changing a factor changes the response. Okay, so I'm going to vary temperature between a high level and a low level. I expect that to create some change in the response I'm measuring. That change we're going to call delta. So delta is the size of the change that I see when I go from a low level of a factor to a high level of a factor. And then what we do is we compare that size of the change we measure to the noise. And so the noise we capture through the experiment through residual error and pure error. And then the larger that signal is to the noise, the more certain I am is that the signal's real. Okay, so let's say that I'm varying a factor, I'm creating a delta. Well, the null hypothesis, that's that H0, says that there is no change. And that's what we test for when we do analysis of variance. So there's a truth, either the changing the factor does create a change in the response, or it doesn't. And then the ANOVA gives us information about whether we think the change we observed is real or it's not. So if the truth is there is no effect, and we run the analysis of variance, and the analysis of variance says you don't have enough information to reject the null hypothesis, you have to retain it, that's okay. There was no effect and we didn't detect an effect. Okay, what if there is no effect, but we end up rejecting the null hypothesis? So the ANOVA says there is an effect. There really wasn't one, but the ANOVA says there really is one. That's what we call the type 1 error, and that's measured by alpha. Okay, you see that directly in the analysis of variance table. So when we look at the p-values in the analysis of variance factor table for factor 1, and that p-value is, let's say, 0.05, okay, that means there's a 5% risk that we're falsely rejecting the null hypothesis. Now, it might be a 10% risk. It might be a 1% risk. Okay, but there's some risks that we're saying the effect is real and it's really not. So that risk we get directly out of the analysis of variance table. Okay, let's say there really is an effect. So the truth is, yes, changing factor 1 from the low level to the high level created a change in the response. Now, if we reject the null hypothesis, that's good. That's what we wanted to do. There was a real effect, and we said there was a real effect. But what if we don't reject the null hypothesis? Okay, that's called a type 2 error, and that's measured by beta. And so beta is the failure to detect an effect when it exists. Now, unfortunately, the analysis of variance doesn't give us any information about what that risk is. Power does. So what power is power is equal to 1 minus beta. So remember, beta is the risk of failure to detect, expressed as a percentage. Now, we want to make sure that if we're running the DOE and there's a real effect, we'd like to be able to find that effect. So we want the power to be high, at least 80% for experimental work. If you were doing some other work like gathering data to submit to the FDA to design a design space you're going to work in, that'd be much higher than 80%, maybe 99%, but much higher than 80%. But for most experimental work, we'd like it to be at least 80%. You can decide on what it is. Remember, if it's low, then there's a big danger you're going to run your DOE and you're not going to find what you're looking for. Okay, so let's look at a little example. So in this example, the golf ball represents the size of the effect. So that's delta. Now, once we run the DOE, delta is fixed. What fixes delta? The levels you choose for your factor. If I'm varying temperature and I'm varying temperature over a very small range, let's say I normally run at 200 and I decide, well, I'm going to run at 199 and 201, the change in the response due to the change in temperature is likely to be very small. So that golf ball would be little tiny, smaller than a marble. Okay, if I push that range of temperature out and say, well, maybe I'll go from 195 to 205. Okay, now I've created a bigger effect due to changing temperature. Now it might be golf ball size. Okay, if I went further, maybe I could make it baseball size or softball size or basketball size. But what happens if I go too far? The experiments fail and I don't learn anything. Okay, so trying to pick the levels of the factors is very important. And that's where your subject matter knowledge comes in. Okay, so anyways, we've created a golf ball size effect. Now we have a certain level of noise in the experiment. Okay, that's represented by the grass here. Now the noise we can do something about in the experiment. The effect's set once we pick the factor levels. Doesn't matter how many times I repeat the experiment, the size of the effect is set. It's golf ball size. But I can do something about the noise. The more times I do the experiment, the shorter I can cut the grass. And so if I do the experiment, let's say once, maybe the grass is twice as high as the golf ball, it's going to be hard to find. It's going to be hard to see my effects. If I do the experiment more than once, I may be able to cut that grass down to where it's the same height as the golf ball. That makes it a little easier to find. If I do the experiment even more times, I can cut the grass down further. Now it's very easy to see the effect. So those three pictures would represent the tall grass would be really low power, the in-between grass would be intermediate power, and the short grass would be a really high power experiment. So how many replicates do we need to do? Okay, well, that's something we can calculate before we do the experiment, but we have to provide some information to do that. So first of all, we have to decide what signal is it important to be able to discover. And so we talk about the minimum amount of change to produce a eureka moment. Okay, Now, you have to be careful. Often when people are doing a DOE and you say, what's important for you to learn, people might say, well, any effect. If I want to know if any effect, no matter how small, I want to be able to detect it. Well, that's unrealistic. You know, that would require running the experiments an infinite number of times to detect any effect. Not very practical. So what you really want to do is say, well, what signal, how much change is important? When would I take action, or when would I spend money? That's what I want to be able to detect. So you have to reasonably pick what delta you're interested in. And then remember, you have to pick your factor level. So if it's temperature, you'd have to pick those two low and high temperatures far enough apart that you expect to create a change in the response equal to that delta you're interested in detecting. And we need to have some expectation of what the noise is going to be. Now, when you've run an experiment, if you've done one in the past, that noise we're talking about is the sigma at the bottom of the ANOVA table. You know, the unexplained variation we can't explain with the factor settings from the design. So that's the experiment, our estimate of experimental error. That's the sigma we're interested in. Okay, so we have to be able to supply what delta we're interested in, what noise we expect. Then we got those two risks. We have to balance those off. What's the acceptable risk to find false effects? We often set that to 5%. Okay, you could maybe set it to 10. I can't see going any higher than 10. Maybe if you really were worried about not finding effects, you could make it lower than 5, maybe 1%. It's maybe somewhere between 1 and 10%. 5 is a number people often use, but there's nothing magic about it. Just seems kind of reasonable. Then you have to set the beta, the acceptable risk for not finding effects. So we often set that at 20%. That's where we come up with power of 100. Because remember, confidence is 1 minus alpha. So when we talk about a 5% alpha risk, we say, well, we're 95% confident that effect is real. Power is 1 minus beta. So we set beta at 20%, and we say, oh, the power is at least 80%. If an effect of the size I'm interested in exists, I'm 80% sure I'll find it. Okay, so let's go through an example. Okay, so I'm gonna use a couple examples in here, and they're drawn from our workshops. I'll have one slide at the end that talks about our workshops. But this case involves highlights from a team that's working using a DOE to try and improve a mouse cell fluorescence assay. And these experiments are performed in a 96 well plate, and they want to improve the amount of fluorescence to make it easier to find the analyte they're looking for. And they're going to study several, in this case, 3 effects. Notice one of the authors is our very own Sherry Kraber, who's monitoring and answering your questions. Okay, so the assay system used to detect cell activity is the cells are pipetted into a well on the 96 well plate. Stimulant is added to induce the mouse cells to express a biomarker. The plate's then normalized with media and incubated for 2 hours. A fluorescently tagged substrate is added to bind with that biomarker. Then we read the plate on a fluorescence plate reader at a specific wavelength. And the objective of this study is to find the settings of the 3 factors: cell number, stimulant, and substrate concentrations that maximizes the signal, in this case, the fluorescence emitted by the plate. So we go through our DOE process. We identify what the objective of our study is. Our objective is to maximize the signal from the assay. Then we have to state that objective in terms of a measurable response. Okay, so our measurable response is the change in the fluorescence. The fluorescence is our response we're measuring. And we say it's important to detect a change of 400 fluorescence units. Okay, so our delta in the response we're measuring that we want to have high probability of detecting is a change of 400 or more. If it's smaller than 400, it might be of some academic interest, but it's not really very important. But if it's 400, that's where we're going to start taking action. So we want to have a high probability of detecting those. Then we have to have an estimate of what the error is. Well, we've measured fluorescence on these cells before. We know from running other DOEs, the sigma we get's about 400. Okay, so in this case, we're looking for a signal that's about the same size as the noise that's present. So that's going to be of intermediate hardness to detect. A delta, you know, the golf ball and the grass are about the same height. Okay, so then we have to pick our factor levels. And so remember, we have to pick levels where we think will generate a change in fluorescence of about 400 units or more. So we pick the number of the cells, cell number between 5,000 and 10,000, the stimulant between 5 and 10 microliters, and the substrate concentration between 0.15 and 0.3 micromoles. Then we select a design. Well, we have 3 factors. We're going to do a 2 to the 3rd, 2-level factorial, and evaluate that design. Aliasing, it's a full factorial, so there aren't any aliases. We'll run all 8 combinations. Evaluate the combinations for safety and responsibilities. When we lay out this design, you know, picking the levels of those experiments independently, they all look good, but what we want to do is look at the design before we run it and look at all the combinations and make sure there isn't a combination that first of all would be dangerous, or secondly we think would be a failure. The experiment wouldn't work, and if we find something like that, we can go back and change the level of our factors, or maybe use a different design where we constrain the design not to go into those regions. In this case, they're all fine. Then finally is we want to look at the power, and we want to have at least an 80% probability for detection in this preliminary study. Okay. So for this experiment, the experimenter suspects the need to replicate this design, but says how many replicates are enough? Well, evaluating power is going to give us the answer to that question. Okay, so these are just instructions from the class. If you have Design Expert, you're probably familiar with them. If you don't, we're just going to set up to run a 2 to the 3rd 8 experiments. Okay, you set up that design, you put in the factors, the levels. Remember, the levels we think are different enough that they'll generate a change of 400 or more. Then we put in the delta, the change in the response, in this case fluorescence that we want to detect. We input the sigma, the noise that we think will be present in the system, and then we click on continue, and then that gives us the power. Okay. Now, with only 8 experiments, that's not a very big N, right? If you compare the low level of a factor to the high level of a factor, you got 4 at the low level, 4 at the high level. Doesn't do much to cut the grass. The power to detect is only about 20%. Okay. Not anywhere close to the 80% we want. Okay, that's not unexpected in a 2 to the 3rd. They're very low power experiments, so we know that we have to replicate. The question is how often. Well, you can just click back and tell it you want to do 2 replicates instead of 1 replicate. You know, it retains all the information about the factors and everything. Then you click forward and you say, oh, with 2 replicates, I get up to 45% power. Okay, so that's a big improvement over 20%. Then you could keep doing that and do 3 replicates and 4 replicates. By the time you get to 5 replicates, you see you've achieved greater than 80% power. Okay, so it's going to be red up until you get to 80% power. And then we change the power measurement in percent to black, assuming you'd want to have at least 80% power. Okay, so now we know how many runs to do. Okay, so here's the summary of all those runs. So if we do just 1 replicate, we're at 19.5. If we do a second replicate, we're at 45. If we do a third replicate, now we're up to 24 runs, we're at 65. Fourth replicate, we're up to 78.9. Now, if these replicates were expensive or time consuming, or there was some other constraint on the number of runs, we might have stopped there and said, that's close enough. You know, if I round that off to a single significant digit, I'm at 80%. But, you know, these are cells on a 96 well plate. The reagents and things we're using are relatively inexpensive. So we can easily do 40 runs. That's less than 1 plate. And that gets us up to our 87%. Okay, so we're going to use less than half the wells, and that gets us up to where we need to be. And of course, adding more replicas would increase the power, but just looking at this, you can see how the power increases a little bit less with each replicate. And by the time you get past this 5, adding more will make it better, but it'll climb pretty slowly. So what does power depend on? Well, it depends on the size of the difference. The larger the difference, the higher the power. Now remember, replicating the design doesn't affect that delta. The only thing that affects how big that difference is going to be is what you pick for your factor levels. Okay, so you have to use your subject matter knowledge, your any other information you have, historical data, maybe even a couple range finding experiments to figure out what levels of the factors to use. Okay, and then the size of the experimental error. The smaller the experimental error, the better. So anything you can do to reduce the experimental error is going to help. For example, when I did real work, working in a pilot plant, we could take samples from our reactors, and we had a little lab. We could do a wet analysis and measure things, and we'd have a certain sigma. Sometimes when it was important and the experiments were expensive, we'd take a sample and we'd bring it over to the analytical lab, and we'd have them use GC rather than our wet analysis, because the experimental error was about 1/3 of what it would be if we did it in our own lab. Okay, and it was cheaper to pay them to do the better analysis than it would to be replicating experiments in a 60-gallon reactor. Remember the sigma, the sigma and the beta are like a teeter-totter. If you try to make one really small, the other one goes up. So you could use a larger sigma and increase, alpha, and increase the power. Okay, and so instead of 5%, you say I'm going to use 10%. Well, if you're more willing to make one kind of risk, then the other risk goes down. So if you make that risk bigger, the beta risk goes down. I don't think that's a very good way to proceed. You really don't want to make either risk, and so you want to pick reasonable levels, maybe 5% and 20%, and then do enough runs to get them to be able to achieve them both. The design you use, the more orthogonal and the larger designs have more power. Okay, so 2-level factorials are orthogonal. We did a full factorial. Okay. So now if we did a fractional factorial, let's say we're studying 6 factors and we're doing a quarter replicate, we didn't have enough power, and we said, okay, that's 16 runs. I'm gonna do those same 16 runs again to get to 32 runs. I'd have more power, but you'd have the same problem with aliasing from a small fractional factorial. So if it was a fractional factorial, before you'd replicate, you'd add more fractions. So you'd say, instead of doing a quarter fraction, I'll do a half fraction. That's going to get us back up to 32. We're going to get about the same increase in power as if we replicated that quarter fraction, and we're going to reduce the aliasing significantly. Okay, so that's just something to consider. And then finally, if you're doing a full factorial, replicating. So replicates give better estimates. By better estimates, it means we were able to decrease the noise, thereby increasing the power. And so we saw that in this experiment, we required 5 replicates to get to where we wanted to be. Okay, so that's replication. Now, what about repeats? Why would we want to repeat measures? Okay, so let's first talk about a repeat. So replication reduces all the sources of variation by a factor of R, where R is the number of times the design's replicated. So when you replicate a run, you're reducing the variation due to the experimental factors varying around their set points, and you're reducing the variation of the measurement because you're measuring each run separately, so you're measuring the same conditions twice. When you do one run and you measure twice, well, you're not reducing the variation of setting the factors because you only set them once, but you are then still reducing the variation of measurement, assuming you do independent measurements, by a factor of M, where M is the number of measurements taken. Okay, so reducing the total variation by any amount increases the signal to noise. So we can increase the signal to noise by replicating the run or by replicating the measurement. Which one makes more sense depends on where the noise is coming from. If most of the noise is coming from the process, then replicating the measurement isn't going to help you at all because you need to reduce the process noise. You got to replicate the runs. If most of the noise is coming from the measurement, then replicating the measurement may be a more economical way to reduce the overall noise than replicating the whole run. So if repeating the measurement M times only decreases the measurement variation, why not always replicate? Well, it almost always costs less to remeasure than it does to replicate. I'd say it always costs less because if you replicate the run, you're remeasuring anyhow. Right? You got to measure it in the first one, you got to measure it in the second one. If you're only replicating the measurement, that means I make only one run, I measure twice. So it's always going to cost less than replication. If most of the variance is coming from the measurement, then this gives you a really economical way to reduce the noise. You get the biggest bang for the buck by just reducing the measurement variation. However, if the converse is true and most of the noise is coming from the process, it isn't going to help. So a repeat is a measurement done again without resetting the system. So repeat measurements then are averaged and reported as a single response. So we don't enter it as 2 different runs because we only did the run once. And we've done the measurement multiple times, so we put the average in. And as we all know, or hopefully we all know, that averages have less variation associated with them than the individuals that go into making up those averages. So all we have to do is measure it 2 times, 3 times, whatever we decide is appropriate, and then we average those measurements and put that number in. If the test is destructive, then what that means is we're going to set up the process once to make a certain part, and we'll make multiples of that part, and then those can be measured independently later. Okay, but we're only going to do the setup of the process once. So let's look at an example. So you probably all know what a stent is. It's a wire mesh tube used to prop open an artery that's recently been cleared using angioplasty. And the stent is collapsed over a small, to a very small diameter. So this is a blown up picture here of a stent where they've blown up the balloon. But normally that would be all squished down and it would be about the same diameter as this catheter that's running through it. Okay, so it'd be all squished down on there. Then they position that, and that's what the two bands are, so they can see those on a scope and position it over where the blockage was. Then they use the balloon to blow up the stent. Then they deflate the balloon and pull everything out, leaving the stent in place. Okay. So here's our design criteria. So we're going to be looking at stent safety and deliverability criteria. Those are our responses, and we want to improve those. We want it to be able to deliver it easily, and we want it to be put into position safely. And so we're going to study a number of process factors. So the safety, those are the ones we're going to look at. There were other responses, but it's quantified by the burst pressure. So when you use that balloon to inflate the stent, you don't want the balloon to burst. That would be an absolute disaster. So we want to make sure that the balloon isn't going to burst. Deliverability is quantified by pushability and trackability. So that has to do with pushing this up and getting it into position in the vessel, okay? And they know from past experience that they have two-factor interactions, and so they're going to require a resolution 5 design. If you don't know what a resolution 5 design is, in a fractional factorial, what that means is you're capable of estimating all of the main effects and all of the two-factor interactions. The 3-factor, 4-factor, 5-factor, all the higher order interactions can be confused with the main effects in the 2 factors, but those are clear of each other. Okay, then they talk about what's important for each one of these factors. So the change in the response for burst of 6 PSI gauge is important. For push, 15 gram centimeters. For track, 10 gram centimeters. Okay. Then they need to know experimental error. Well, they've run these tests before on production units. They kind of know what the variability is in measuring each of these. And for burst, it's 7 PSI gauge. For push, it's 28 grams per centimeter. And for track, it's 6 grams centimeters. So if you look at the delta to sigma ratios, which one do you think will be the hardest one to achieve the power you want? Well, the smaller the delta relative to sigma, right? The delta is the golf ball, the sigma is the grass. The smaller the delta is relative to the noise, the harder it is to detect. So it looks like track will be the easiest, then burst in between, and then push will be the hardest. Okay, so here's the factors. These are a number of factors. So they're talking about the balloon wall thickness, the waist length, the waist wall, the wing folds. When you fold that balloon up, you can kind of fold it. If you think of 3 wings or 5 wings, inner diameter. So all of these, for us, it's not too important. For them, it's important. And remember, when you're picking these levels, you have to be thinking about picking levels that are going to generate a change large enough that we're interested in it. So you have to be thinking about what's that going to do to burst, what's that going to do to push, what's that going to do to track. And I want to be able to generate changes in these on this order of magnitude. Okay, and they go through and do all of this. Okay, so then we evaluate the alias. It's resolution 5. That means we can get all the main effects and 2-factor interactions. We'll have to be looking at power, examine the layout. This was an interesting one because they found when they went through before they ran the experiment, they went through and looked at all the combinations. They found some combinations that were impossible to make, not on this screen, but on a previous iteration. They had to go back and adjust some of these levels to make sure they got all combinations that could actually be physically assembled. So that required some changes. Then they get to selecting a design and they say, well, if I want to run a regular fraction of a 2 to the k minus p, a fractional two-level factorial, for resolution 5, that's going to require 128 runs. Well, setting up to produce these catheters with the stents and the balloons on them is a timely and expensive process. And so they didn't have the time nor the money to do 128 runs. So they said, okay, well, what's our next alternative? Well, they chose a minimum run resolution 5 design that required less than half, or only 56 runs. So they decided, okay, that will still allow me to get the main effects and the two-factor interactions. Doesn't require as many runs. But now, when you go to less than half those runs, what do you think happens to power? Well, it's going to be smaller. Will it be enough? Well, we can evaluate it and find out. Okay, so you go ahead and build the design, and here's the same ratios we looked at earlier. Okay, with the delta and the sigma. Delta, what we're interested in, the sigma, again, coming from historical data from testing that's been done in the past, and the push and the track. Okay, well, remember this was the easy one, the track, so we weren't too worried about that. You know, we've got really good power there. The intermediate one for burst, those are good. You know, those are kind of the threshold we'd like to be at, you know, at least 80%. When you get to push, it's quite low. You know, we're just bordering 50% for all of the main effects. Okay. So what we do is we go back and we look at this now. In medical device industry, they're pretty careful to always do gauge R&R studies on all their testing. So we actually had a good handle on how much of the variation is associated with each of these tests, just the measurement part of the tests. And then we knew from production data what the total variation is, so we could partition the variation into what's due to the test, what's due to the process. Okay, so that's going to help us out. So increasing the design size how do we increase power? Okay, it's too low for push. So if we replicate the design, that gets us up to 112 runs, just replicating that design. Or we could use the 128 run fractional factorial. That would have been about the same number of runs, so the power would have been maybe a couple of percent higher, but it would have been essentially equivalent. That gets us up to 82%. But remember those runs were not only costly, but the big thing here was they take so long to run. It would push the development time out way too long. Okay, we could say, well, maybe we're not interested in 15 grams. We could increase it. Maybe if we went to 30 grams, that would change the delta sigma. It'd be easy to detect. Yeah, it would be, but 15 is where we're going to start seeing trouble. And so we need to know that. Then the other one is, could we decrease the noise? Okay, so basically we're looking at this and saying, is this a reasonable delta to look for? And is there anything I can do to reduce this noise? Because either increasing this, that'll increase this ratio, or decreasing the denominator, that's going to increase this ratio. Okay, by partitioning the variance, we know how much is due to the measurement from the gauge R&R studies, and we know how much is the total from the historical data. We can figure out how much is process and how much is measurement. We determined that the push measurement contributes 75% of the total. So 75% of this 28, not really this 28, but if you squared this, 75% of this number squared is contributed by the measurement, and the other 25% is coming from the process. So repeating the test, just remeasuring, will give us a big increase in power. Okay. So we know that this overall is 28. We know what the measurement is from the gauge R&R, so we can figure out what the process is. And we figure out that this is how the partition of variance breaks down. This number squared is this. This is about 14. Is that right? I think, yeah, that's about 14 squared. So that sigma is about 14. This sigma is about 28. That's about 14. This one would be about 24 squared. Okay. So then by the central limit theorem, we know when we repeat something, the average has less variation by the number of repeats. So the variance of the measurement can be reduced by m on this average. Okay. So we said, okay, we'll do 3 repeats. Let's do 3 repeats of this. So then our overall variation, well, we haven't affected the process because we haven't repeated any of the runs. We're just repeating the measurement. But when we do this, that gets us down from this 580, excuse me, from this 784 down to 395. So that's about 400. That's being generous, about 800. So we reduce the variation by about half by just repeating the measurement, not having to redo the run. Repeating the measurement doesn't take much time at all. If we had repeated the runs, the whole design became untenable because of cost and the amount of time, mainly the amount of time that it would take. Okay, so that reduces our overall variation from 28 down to 20, 19.9. That increases our delta to sigma up to 0.75. So if we go back, let's go back. And I changed this from 28 to 19.9. Okay, so now I'm going to put in the average of 3 measurements. Now the variance associated with the standard deviation associated with that average is going to be 19.9. So I measure it 3 times, put in the average. Okay, that gets my power up to about where I want it. You know, I'm up to rounding any of those off, you know, you're at 80%. You're 70, looks like about 78% all the way across. Okay, and if that wasn't good enough, I could go back and add another run. Now, of course, each run you add increases the power, but it increases it less than the run before did. But I was curious, so I went and did that. And if you put in a 4th replicate, that gets you up into 83 was the lowest to 83.8. But they decided this was close enough. Okay, close enough. This is the design they ran. Okay, so summary, replicating the runs reduces the system error from both the process and the measurement. Repeating the measurement only reduces the measurement error. The magnitude of each of these errors and the relative cost of replicating runs versus repeating measurements dictates which will give you the most bang for your buck. Remember, when you replicate the runs, you are repeating the measurements because you have to measure on the new runs. Okay, so let's recap. As shown in the mouse assay case study, power was increased by replication, that is adding more runs. In the stent case study, repeating the measurement proved to be more cost effective and really much more time effective way to reduce the noise. These 2 techniques can be combined to reduce cost and variation. So sometimes you might say, I'm going to replicate all the runs. And for this one response, I'm also going to repeat the measurements and put in the averages for those replicated runs. So replication reduces the total variation by a factor of R, where R is the number of times the design's replicated. So you're replicating the run, you're reducing both the process variation and the measurement, where R is the number of design replicates. So it reduces the total variation, increases the signal to noise ratio, increasing the signal to noise ratio increases the power. Repeating the measurements, that only reduces the measurement part, okay? And unless the measurement makes up a large percentage of the variation, it has to be more than half, or it's not very effective just repeating the measurement. So the measurement has to be greater than half of the total. Doesn't help much. But if it is greater than half, it might be worth exploring and a much more economical way to increase the power. Okay, so remember this presentation will be posted on our website. There's also other presentations there. If you want to learn more about power or other topics, you could look through those. If you have any questions that Sherry hasn't answered yet, or you haven't thought of yet, but you'll think of after the webinar is completed, be sure to send those to stathelp@statease.com. We do offer training. If you want to learn more about DOE, we have modern DOE for process optimization, mixture design for optimal formulations. We do both online classes that you can take, or we can do on-site classes or private online classes. Sherry knows a lot more about them than I do. She's the workshop coordinator. So if you have questions, you can send those to workshops@statease.com. We have a DOE summit coming up. Before COVID, we used to do these as live summits. Now we're doing them online. We have an amazing list of speakers from the industry, from the military, and from academia. Registration is free. If you had come to one of our live ones, it wouldn't have been free. So I've actually found during the COVID times, I've been able to go to more summits than I was able to when I had to pay for them and travel to them. So that's, in a way, it's kind of a good opportunity. And you can just register on our website at webinars for the online DOE summit. That's September 28th and 29th. Otherwise, I want to thank you for attending. And remember, there will be a copy of these slides and also a recording of the webinar available on our website. So again, thank you all for attending and have a good day.